Hi folks, welcome to those of you tuning in for a review session on domains, composition of function or combining functions, transformation of functions, piecewise functions, and average rate of change. So there's going to be a chat box over on the right hand side. If you have any questions during this time, please feel free to kind of drop them in there. And these are just altered questions from what I've seen popping up, either where there's issues in the class or where someone's emailed a problem. So I've just altered some numbers and things like that, but mainly same ideas as to what you might be seeing and what kind of questions you're asking me. So without further ado, we'll get started. And once again, that chat box over on the right hand side, just post those questions right in there and I'll try and address them as we kind of move along. So the first one, let's find the domain of the following functions. You have f of x equals the square root of x squared minus 7x. So when we look at this, what do we need to do? Well, we need this stuff underneath the root to be greater than or equal to 0. If not, we're talking imaginary numbers and we can't have that when we're graphing. So x squared minus 7x has to be greater than or equal to 0. So how do we solve this inequality? Well, first off, we set it equal to 0. So we get x times x minus 7 equals 0, because notice we have that equals point right there. And so this means x equals 0 or x minus 7 equals 0, which is the same thing as x equals 7. Now, some of you may remember this from college algebra. Some of you may not, but that's okay. So what we do is we make our little number line. We put 0 here, we put 7 here. And we know that the function, so when we have x squared minus 7x sitting up here, here's your x values down below. We know when we plug 0 in, we get 0, and when we plug 7 in, we get 0. So what we want to see is if it's negative or positive for when we plug in other values. So for example, if we take a look at this, let's plug in negative 1 and see what happens. So when we get negative 1, the quantity squared minus 7 times negative 1, what do we get? Well, notice that would be 1 minus a negative 7, so that makes plus 7, so that equals 8. Now I'm not so concerned on the value being 8. What I'm concerned on is this interval from negative infinity to 0. What's the behavior? Is it positive or is it negative? But notice here we have positive 8, so that makes this positive. Okay. In a similar manner, our next interval that we're going to check is from 0 to 7. So pick a number between there. If you notice, we could try 1. So if we go 1 squared minus 7 times 1, notice we get negative 6. So that means all those within this interval will be negative. Okay, in a similar manner, we want to check the next interval, 7 to infinity and beyond. So when we go here, pick a number, say 10. So when we go 10 squared minus 7 times 10, notice we get 30. That's a positive number. So all of these will be positive. So now taking all of this and putting it together, I'll erase this, the little numbers that we use, because that's not as important as our final answer here. So we now have all those values, whether they're positive or negative. Notice what we care about is this greater than or equal to 0, meaning it's 0 or positive. So yeah, we actually have a solution then. So our cutoff, it will be right here on 4, moving that way. So if we're drawing this, we put a solid dot and then we draw our arrow that way. And then we put another solid dot right here and we draw our arrow to the right. So how do we actually write this domain? Well, this would be from negative infinity to 0, and we want to include 0, so that's where we use a bracket. And then we use this union symbol, and we take it from 7 to infinity. Okay, and that's our final answer. Okay, so when we have roots that are even roots, so square roots, fourth roots, sixth roots, so on and so forth, that's the process we use. We just set whatever's underneath the root greater than or equal to 0. You'll run into actually a logarithm later on. We'll talk about that, I think, in lesson 5. And so when we get to that song and dance, there's going to be another domain thing we have to check, and it's basically setting the inside of that logarithm greater than or greater than 0, so strictly greater than in that case. And then this g of x one, we have something else that we have to worry about. Now notice there's two parts. You have a numerator and denominator. But what can't we do? Well, notice we can have any type of number up top in the numerator. That's not going to be any problem. The problems occur when this whole denominator business equals 0. So what can't happen here is we can't have 2x squared minus 11x plus 15 cannot equal 0. So yeah, and the question is, will we be able to watch this after the live stream? Yes, you can watch it again and again and again, however many times you want. So if you see it one time and you didn't quite get it, obviously ask a question while I'm here. I won't be able to go back and answer the questions, but if you want, you can view this at any point in time. So you'll just see me kind of covering the problems. I'll go through them a little bit quicker if there's not questions, and if there's questions, I'll elaborate a bit more. So whatever works for y'all. So great question. To keep it going, so we don't want this to equal 0, so actually the way we do it is we set it equal to 0, see how that works, and then we'll know what values it can equal. 2x squared minus 11x plus 15. What happens if this were to equal 0? When does it equal 0? Well, this thing can be factored. So you have a 2x and you have an x, right? And now that you have that, where do we go from here? Well, we notice it has to be a negative 11x but a positive 15. So we have to put a minus 3 and a minus 5, or a minus 15 and a minus 1 somewhere. Okay, so let's see, how does this work? Well, if we put a minus 5 on this and a minus 3, and we use our FOIL method, notice those two multiply to negative 6, and these two multiply to negative 5x, or so negative 6x and negative 5x, that makes negative 11x. So there's our factors. That's a perfectly good way to factor it. It's not the only way, though. You could use, to solve this, you can actually use the quadratic formula if you remember that as well. But factoring is going to be a little bit quicker if you remember the factors. So now just set each factor equal to 0. And some of you may be able to do this in your head. That's totally fine. So notice we get x equals 5 halves and x equals 3. In terms of what that looks like, 5 halves, notice, is 2.5. So you have 5 halves sitting right here, and then you have 3. And those are open circles, and then everything else on either side is shaded in. Okay. So what does this look like? When does this, so x cannot equal 5 halves nor 3. And if we're writing our answer in interval notation, not saying you always have to, sometimes we have the shorthand just like we had up above. So that's a valid final answer. Another valid final answer would be negative infinity to 5 halves, open parentheses because we don't want to include the 5 halves. We go 5 halves to 3, once again open parentheses because we don't want to include either of those endpoints, and then 3 to infinity. So that's also a valid solution. Okay, so I don't see any questions on the domain. Hopefully that clears up any questions you might have had. Remember, fractions, we're only looking at the denominator, just finding when the denominator doesn't equal 0, because you can never ever divide by 0. Actually, if you want to have some fun, if you have Siri on your phone, ask it a question about divide by 0, see what it says. So there's some fun little bits that you get from time to time. At least I think that was on the iPhone 5 or 6 or something like that. So if not, don't worry about it, no big deal. But moving forward, we want to start combining functions. So what does this look like? And the reason why we're stopping to combine functions, if you're struggling with transformations of functions, a lot of that stems from the idea of combining functions, right? So let's take a look at how to combine them, how that works. First off, we have this composition of functions. Yeah, so actually coming up, so Catherine asked the question, can you explain horizontal versus vertical compression and stretching? Most definitely, I have that right after this. So this is kind of the segue into that section. I'm trying to make sure that you all are able to follow this, because if you aren't able to follow how to combine functions, you aren't going to be able to follow that next bit. So that's all. I'm just trying to set it up to kind of build to that point. Okay. So yeah, moving forward on this one, if we have f composed with h of 1, how does this thing look? There's a few different ways to approach this. The way I do it is I just try and make it a little bit simpler in terms of getting rid of that little open circle. Some people think that's multiplication. That's composition, though. So you can write this as f of h of 1. And what does that mean? Well, it means we take, in this x, we're going to put the 1 right there. Okay? And so what happens then? Well, this becomes f of h of 1 is just going to be then the square root of 7 times 1 plus 2. So, and if you just plug that in, you get f of the square root of 9. And notice that's f of, well, square root of 9 is just 3. So that looks a little bit more familiar, hopefully. And so what's f of 3? Well, if you look, that means we're going to plug in, so f, we've replaced this x with 3, so that means we're going to plug in for those two x's with 3. So that means we have 3 squared minus 7 times 3 plus 3. So that's 9 minus 21 plus 3. And so 9 minus 21 should be negative 12, and plus 3 should be negative 9, I believe. And that's our final answer for that one. Okay, we can do a similar thing in terms of g composed with f of x. There's a couple different ways to do this if you want. So g composed with f of x. So now we have an x thing in there. So that means g of, well, what's f of x? That's just x squared minus 7x plus 3. So what the heck does that mean? Well, it means when we go to the g of x function, wherever you see those two x's, you're going to replace it with this whole function. Now, you could have just put 4 minus 5 times f of x, and then f of x, the quantity cubed, plus 19. That's also fair and square. Either way, whichever way you want to solve it. And you don't have to do these extra steps, but just want to try and illustrate what's happening here. So this is 4 minus 5 times. So now we got to replace that x with this whole bit of business right here. X squared minus 7x plus 3 all over. So instead of x, we want to replace that with x squared minus 7x plus 3, which is just f of x, by the way. And we're cubing that thing. And then we add 19. And that's it. You're done. Okay. So now finally to this last one. And why am I focusing on this last one? This is the kind of ideas that's going to be happening in transformations of functions. Just an FYI if you wanted to see what's happening. So say we had that graph of h of x. Another way we could write this is 4 times the quantity x minus 1/2. Now, why is that important? Well, what this tells you is if we take the graph of h of x, soon enough, and I'll talk about it a little bit more, this is a shift. So this is right 1/2 units. And since this is on the inside of the parentheses of our function, what this 4 is going to do, that's going to be, it's tricky on these because it's a horizontal compression. If it's outside the h, that's when we're talking vertical stretches or compressions. But since the 4 is on the inside, it does kind of this reverse process that's kind of tricky. So since it's greater than 1, it's a compression, and it's a horizontal compression by a factor of 1/4. And we'll talk about this a little more in a second. But for those of you kind of seeing it. Oh, so yeah, so the question was, do you not simplify the second equation, distribute the -5, etc.? You can. It's really no big deal if you want to. Unless the problem's asking you to, I wouldn't, to be honest with you. And a lot of times what you'll see in your problems, it'll be like g composed with f of 1. So now if I had g composed of f of 1 and I had this function, I'm just plugging in 1 wherever I see an x. I'd hold off from simplifying unless it forces me to, or unless it's talking about inverses. And I can talk about inverses towards the end of this too as well. So I mean, if you want to see stuff on inverse functions, if you're struggling with that, I'm happy to handle that as well. So I did see one question, so I might toss in one question real quick. I don't have it written down yet, but I can definitely toss in an inverse function. That's where you really do need to simplify, but otherwise, I just leave it as is. So, but if it does say simplify, yeah, you can distribute, and so to kind of show you here, you take the 5, you distribute that to -5, I should say, and distribute that to each term. And then this, with it being a trinomial, in order to cube it, I'd write it out 3 times and kind of go about that. So, oh, okay, so see, yeah, inverse function, please. Yeah, just remind me at the end. I'll toss one in there. I don't have it written yet, but I can do that real quick. That doesn't take much time at all. So, yeah, we'll talk about inverse functions, how to find them, and stuff like that. So, this h of 4x minus 2, back to this. So what that means is we're going to take wherever we see an x in this h of x, take a guess as to where we'll place this. Well, we'll replace this with 4x minus 2. So this just becomes square root of 7 times 4x minus 2, and then plus 2. Now, Josh had asked there, oh yeah, should we simplify? I wouldn't unless you really feel like you have to, but if you want to, like this one isn't too bad. So you distribute that 7 to both parts. So it's going to be 28x. And notice we'll have minus 14 plus 2 makes minus 12. And there's your final answer. Now, this is going to be harder to determine the compressions and all that stuff based upon our original function because of the simplifying process. And so that's why I kind of revert back away from simplifying for right now. It's something later on where we're going to see it's nicer to have it kind of left alone in order to determine those compressions and stretches and all that jazz. So, transformations of graphs, what the heck is going on with that stuff, right? That's all sorts of trickiness going on. So there's a whole bunch of scenarios going on at once here. Let's say we have a function f of x, right? And you see I've done all this junk to it with the key component I want to talk about. They're all non-zero. So everything I'm talking about here is non-zero. That's actually quite important. So let's discuss what's happening here. So the a value, first off, if a is less than 0, so what does that mean? If a is less than 0, let's think about that. That just means it's a negative. We have then the function is reflected over the x-axis. Okay, so now if it's happening where you have that less than 0, so you'll actually see, you notice I didn't put it in here, but it will look mostly like the negative a. That's where people kind of get confused, but I'm just going to say a is less than 0 because it's just some constant. So if it's less than 0, meaning negative essentially, then it's reflected over the x-axis. Now there's other components as well. If the absolute value of a is greater than 1. So notice this is outside the function. What's happening? Then the function is stretched vertically away from the x-axis. So the reason why I put absolute value, so like, let's say you had -2, right? So what that does, that's two things. First, it would reflect over the x-axis, and then it would stretch vertically away from the x-axis if it was, say, a equal -2. So now, the other component that we have to worry about is if the absolute value of a is between 0 and 1. So then the function is, rather than stretched, we say it's compressed vertically toward the x-axis. So think of numbers like 1/2, for example, or 1/3, right? What we're doing is we're starting to squeeze that down. Or think of if you had both your hands, you had it on top of the function and then on the x-axis. You're pushing that function towards the x-axis. Or on the top and bottom end of the function, you're pushing it, compressing it towards that x-axis. That's what we're basically getting at there. Okay, so that takes care of the A situations. The next bit that trips people up is, let's look at this K right here. And then the B and the C are a little bit easier. So first off, if K is less than 0, so this is going to follow pretty much a similar suit, then function is, well, notice before, if it was on the outside, it was reflected over the x-axis. Can you take a wild guess as to where we'd be reflecting in this case? Surprise, surprise, it's going to be the y-axis. Okay, so I know this might look kind of funky because I'm using all these letters right now, but I'll kind of bring it home with an example. Other scenarios. So now here's where it gets tricky. Oh, and before I should put away from x-axis by a factor of the absolute value of A, and this is also by a factor of the absolute value of A. So now in this case, here's where it gets kind of everything that's inside the function. So notice all these components are inside of the function. When you have this inside part, if the absolute value of K is greater than 1, then the function, now before when we had greater than 1 it was stretched and it was vertically. Well, it's going to be horizontally because it's inside the function. But it does just the opposite of what you'd expect. In this case, it's going to be compressed, and it goes horizontally. So if we're going horizontally, we're going toward, now the horizontal, when we're pushing things towards each other, the y-axis. Now here's where it gets a little bit trickier too. By a factor of, it goes 1 divided by that absolute value of K. So it's, yeah, and so you all got the y-axis, that's awesome. Yeah, so it's the 1 over K factor in these cases. So when it's inside the function, that's when we have that 1 over K business. I know that trips up a lot of people, so just make sure you're aware of that. So in the other case, if 0 is less than the absolute value of K and it's less than 1, then the function is stretched horizontally away from the y-axis by a factor of still that 1 over K. Absolute value of K, I should say. Okay. So now the next piece. You see the plus B, I put plus C. Now it changes if it's minus, it goes in the opposite direction for each. So the plus B, all that means, when it's on the inside, it's shifting left or right. Plus does kind of the opposite of what you'd expect. It shifts left B units. So if it was minus B, it would shift right B units. And this plus C is a shift up C units. Okay, and if it's minus C on the outside of the whole function, that's going to be down C units. Now this does get trickier when our functions get more complicated, right? We start off with simple functions and then we work to some more complicated things. I'm going to do a generic one for a general function, see if we can describe what's happened to the original function. And then I'm going to see an example and hopefully we can work that out too. So I'm going to erase this and I'm going to just put real quick a function with real numbers this time around. And I should warn you that you need to be kind of careful with some of these in terms of the order in which they happen. So let's say we have a negative 4 f of 3x minus 7. Let's go plus 19. What do we do? So the first thing what I'd recommend is looking at this negative symbol, and that tells you you have a reflection. So we'll reflect f of x over the x-axis, followed by, what does this 4 on the outside do? Well, that's if you think the 4, so that's a greater than 1 scenario, so that's a vertical stretch away from x-axis by a factor of 4. What does the 3 do now? Well, that's a horizontal. Now remember, it's greater than 1, so it does just the opposite of what the scenario for when it's outside the function does. So this is a horizontal rather than a stretch. It's a horizontal compression by a factor of, now we take the reciprocal of this, so that's 1/3 toward the y-axis. And you might hear some different language, but this is the general idea. And then what's the inside doing here? That's a shift. Well, remember, if it was plus, it was to the left, so this is a shift right 7 units. And then the plus 19, and then we shift up 19 units. And so this is where it can get confusing. Notice I have a general function f of something, right? And I've manipulated that. So what does it look like in more of a realistic scenario where we're given the function and then we work with it? Okay, so I'll kind of take a look at that now, since I don't see any questions. So let's consider the function f of x equals 4x cubed minus 7x plus 2. Explain the series of transformations performed on f of x to obtain the function g of x equals, you have negative the quantity 4 times 2x, that quantity cubed, minus 7 times 2x, and then plus 2. Okay, so notice what's happened here. Well, how do we move from f of x to this function? So what we need to do is try and figure out, what do we do to f of x? So notice the first thing, the x's have been replaced with 2x. So we'll start with that. So you have f of 2x. What does that do? Okay, well, if you recall, this is a horizontal compression toward the y-axis by a factor of 1/2. And notice, just in case you aren't sure what that looks like, that's 4 times 2x, the quantity cubed, minus 7 times 2x plus 2. And hopefully, Josh had asked the question earlier, do we need to simplify? This is part of the reason it's nice when we don't have it simplified. We can see that a lot easier. Notice if I simplify it, a little bit harder to catch, because when I cube that 2, I get 8 times 4. I have a 32 there, x cubed. And then I have a minus 14x, right? That's not the same number all the time, and that's why the horizontal compression behaves really different than other scenarios. So, oh, and I should say a horizontal compression of f of x. Okay, so now what do we do afterwards? Well, notice that negative times this whole quantity. Well, that whole quantity is indicated by that. So then we have negative f of 2x, right? So that should be negative times this whole quantity, 4 times 2x, the quantity cubed, minus 7 times 2x plus 2. And so what does that do? Well, notice it's outside the whole thing, so that's a reflection over which axis do you think? So let's take a second and see if we can catch it. Reflection over which axis are we getting into? Well, it's a reflection over the x-axis. Very good. Great job. So Catherine, you were the first one to indicate it. Since you're the first one to the punch, that's an eagle egg right there. So you can shoot me an email and you'll get a bonus point. So good job on that. Now, moving forward from here, what do we do with that last step? So we have a plus 9, and so notice all we do is we take negative f of 2x, and then we add a 9 to the outside, and so in this case we shift up nine units. Okay, so you'd get this negative 4 times 2x, the quantity cubed, minus 7 times 2x plus 2 plus 9, and notice we have our full function. So there's your steps 1, 2, and 3. So now you see how we can actually write down the steps in order. The next trick to this trade here is actually given the steps, what does that look like, right? Yeah, that's a little bit tricky. So I'll kind of go through how we work those out, because order of steps actually does make a big difference. So in this case, let's consider the graph of f of x being the absolute value of x. And the graph of g of x is obtained by taking g of x and applying the following taking f of x, I don't know what I was writing there, and applying the following transformations. Sorry about that. Okay, so we're going to stretch vertically by a factor of 3, then away from the x-axis, then shift up 7 units, reflect about the x-axis, then shift left 9 units. Okay, so the steps in this are important in the indicated order, and this is where people get tripped up because it's a little bit different than before. So stretch vertically by a factor of 3. What do we do to f of x to stretch vertically? Well, if you think about it, and we're going a factor of 3, so that means we go on the outside of f of x and we go 3 times f of x. So what the heck does that look like? Well, 3 times f of x equals 3 times the absolute value of x. Okay? Now what I'm going to do is I'm going to call this new function f1 of x. So f1 of x equals 3 times the absolute value of x. That's a 1. Don't let your eyes fool you there. That's a perfectly drawn 1. So now step 2. What do we do? Well, we're going to take this most recent function, so f1 of x, and we're going to shift up 7 units. So what does that do? Well, on the outside, because inside is horizontal shifts, so go f1 of x, and then we go up as plus, so plus 7. And if you notice, that's 3 times the absolute value of x plus 7. So we'll call this function f2 of x on step 2. So 3 times the absolute value of x plus 7. Now here's the part that trips people up. What most people say is they just put a negative out in front of that absolute value of x, and they're good. That's where the order is important here. Notice before we reflected right after our compression horizontally. In this case, notice we're shifting this whole graph. And so for example, what's happened is you take the absolute value of x, which looks like a v, and that's a perfectly drawn v once again. let me change colors so we can kind of see. There's the original, and then for this we'll color 3x. We're going to stretch vertically, so you get something. I'm not saying I'm not so worried about the values themselves. So that it's getting skinnier essentially is what's happened. When you stretch away from the x-axis, you get something skinnier. And so let me draw the next one in purple. So when we shift up, I should have the same drawing as the pink one, but it's just up higher. Now think about what we're doing. Okay, so with our next drawing, let me do light blue. We're reflecting that graph that's purple over this x-axis, right? And so when we reflect that over the x-axis, here's what happens. You get a graph that's the same skinniness, but notice rather than shifting up 7 units, now we've shifted down. And so how do we do that? Well, what we do is we take negative f sub 2 of x. Right? We take the most previous one and do that. So now this is where you get the negative times the quantity, 3 absolute value of x plus 7. You might say, well, Josh, why does that work? Well, notice when we distribute that negative sign, you get the negative 3 absolute value of x, but you get the minus 7, which indicates reflecting over about the x-axis at that point. So in this case, we'll call this f3 of x, and we'll say it's negative and then 3 absolute value of x plus 7, or you can also say that's negative 3 absolute value of x minus 7. Either way it works, but you got to be careful. Notice we're putting parentheses around that most previous step. That's where people trip up. They forget the parentheses. They just think it goes to the f of x. No, it's the previous term. And hopefully the graph drawing helps you with that. So now the final piece to this puzzle, let's see, we'll go black here. So we want to shift left 9 units. So I'll finish with a graph that's somewhere off, and well, that graph's supposed to be the same, but somewhere off in here, right? So it should have the same value there. And what we want to do for step 4 is we're going to take f3 of x. Well, in order to shift that left 9 units, we go inside the parentheses, so we go x plus 9. So everywhere we see an x, we're going to put x plus 9 now. So this goes negative 3 absolute value. Oh, I'll do it this way, in parentheses first. Negative the quantity 3 times absolute value of x plus 9, and then plus 7. If you wanted to write it another way, remember this is also negative 3 times the absolute value of x plus 9, minus 7. So both of those are equivalent, but you might have 2 different ways they've written it, okay? So hopefully that makes sense. Does that clear it up a little bit for the transformations? I'm going to do one more, but hopefully that gives you an idea in terms of the sequence of all these things, how we're working this out. So you saw a stretch pretty early on of the vertical stretch. Let's try another. So now we're going to deal with f of x equals square root of x. What happens here? So on our step 1, same thing, we're doing a sequence of these. And by the way, if I had started with a horizontal, well, actually, I can, you know what, I'll do a horizontal here in this case. I already did a vertical one, so you saw how that happened on the outside. Just so you can see this. Stretched. Horizontally by a factor of 2. No, I guess it doesn't matter either way. So step 1, reflect over the y-axis. So what have we done when we reflect over the y-axis? Well, we take, first off, our square root of x, and we're going to go f of, if we're going y-axis, that goes on the inside, so that's f of negative x. So in this case, we get square root of negative x. And so we'll call that f1 of x. Okay. Step 2. So we're going to take f1 of x, so that's a check mark on that one. Shift right 7 units. So we're going to take f1 of x, and now what do we want to do? Well, to shift right, we go minus on the inside, so we go minus 7. So now this becomes the square root of negative times the quantity x minus 7. And notice that's f2 of x. So, oh, great question. So the question is, wouldn't that be an imaginary number like with I? Well, it would depend. What it actually does is it switches the domain, and I'll kind of show you from a graphical standpoint. So if you have a graph, so yeah, on the previous question, I'll go back to that in just a second, and I wanted to address the imaginary number business here. So we start off with the square root, right, which looks something like that. Okay, notice the domain of this function is x greater than 0. When we go to, let's say, f1 of x, what do we do? Well, when you reverse it over the, oh, whoa, that's horrible. When you reverse it over the y-axis, what you've actually done is just switch the domain. It used to be x greater than or equal to 0. Now it's x less than or equal to 0. So it's a great question, and actually I'm glad you asked it. So now, in the previous question, I'll go back real quick. So the question that's popped up now, if I can get back to it, it says, on the previous question, it seems important to distribute the minus before coming up with the final answer. Yeah, it really isn't necessary in some regards. So if we go back to this, we see that, hey, this is a good, valid final answer. But also, this is a good, valid final answer. And I don't have an end-all, be-all in terms of how your quizzes are going to look, because they'll actually use both. Sometimes they actually simplify it. Sometimes they have parentheses inside of there. So every single one of them is going to have some little twist to it. I want you to be aware of both in how they're indicated. It's the same thing with what happened on the previous one, even before this. Notice how that 2x was in parentheses, so it didn't simplify it in that case, right? And we left the negative out in front. So that made it a little bit easier for us to handle. You just have to be aware of what's the associated transformations along the way, right? It's tricky, I agree. But with practice, you can do this, and especially the ones that list them out, it's a lot easier to kind of go through the motions in terms of figuring out what's going on. So now, I'll kind of continue with the drawings in terms of what's happened. So we shift right 7 units. So now we've taken this graph and kind of gone this way, right? So we have the same graph, just shifted right 7 units. Now what happens? Well, we want to shift down 8 units. So step 3, we take the previous graph, and so we're going to take f2 of x, and if we shift down 8 units, we go minus 8. So notice that's going to be the square root of negative x minus 7. Close that off, and then minus 8. Notice the parentheses in there. That actually is, if you distribute that minus sign inside the parentheses, you get square root of negative x and then plus 7 underneath the square root. So the fact that I left that there is actually kind of useful. So now what that graph would look like, I shifted down 8 units, so go somewhere here, and then you get that same sort of looking graph. And we'll call this one f3 of x. Now, I want to emphasize something here too. When you take a look at this piece, the f3 of x, notice our domain. With the shifting right 7 units, so this ties back into the question about imaginary numbers. Our domain is from negative infinity now to positive 7. So with all these shifts, we're just changing domain left and right. And that ties back into the beginning part, right? We had that domain with the square root. What the heck's going on there? The reason behind checking the domain, I mean, all we're doing is transformations of some function. In this case, it's the square root. So all these ideas kind of tie back in together. Now, let's see what happens with this next one, because this is where things get a little haywire. Stretch horizontally by a factor of 2. I should write towards y-axis, or sorry, away, because we're stretching away from. So notice what's that going to do? Well, that's going to take this whole graph and kind of further it out, right? So now, in order to do that, it's counterintuitive in some regards. So you think you toss in a 2 into this f of 3x, but remember, in order to do the horizontal one, it's the 1 over whatever value. So what we have to do is go 1/2 x in that case, right? That's the tricky step in this part. So we go 1/2 x. So now what does that look like? What the heck did we just do? So this is square root of negative. We replace the x with 1/2 x. And why is that? Well, notice what that would do. I don't have enough room on here, but to stretch it away, I'm going to take that dot, and basically that should double in length away, right? Well, if I put 1/2 x in there, minus 7, notice that x now becomes, instead of 7 to be the 0, it's going to be 14. And that's exactly what we're looking for. So, kind of tricky, and the order is important again. So then minus 8. And so now this f of 4x, what does that equal? Well, that's the square root of negative 1/2 x minus 7, and then minus 8. Okay. Great question. So I see, how did I know to use 1/2 for x? That goes back to, remember that list? I don't know if you were writing it down and I erased it. Let's go back. One more. Come on. Ah, there we go. Okay. So remember this k business right here? If our k ranged between, and I put absolute value, 0 and 1, we stretch horizontally away from y-axis by a factor of 1 over the absolute value of k. So in terms of what happened here, I didn't know what the k value was, but I knew what this factor was right here. We knew the factor was 2. So all I did was set 2 equal to the 1 over the absolute value of k. And since it's positive, I don't have to worry about the absolute value. So how do we solve for k? Well, you multiply k over on both sides. So you get 2k equals 1. And then you move that k back on over, you get k equals 1/2. Okay? And so that's how I knew to plug in k equal to 1/2 inside of there. Hopefully, does that make sense then? Just let me know. If not, I'll try and describe it a different way. So it's just using that property. There's a whole slew of them, and we're using those over and over again. So good. I'm glad to see that made sense. So now for the next step, you're welcome. We just have to reflect over the x-axis. Okay, so we've done all this junk. Now we got to reflect this whole thing over the x-axis. So, and I didn't try and draw the stretch horizontally because I can't quite do that. I run off the screen. So hopefully it makes sense thus far. And it might help you to actually draw the graphs. I don't know. That tends to help me personally, but it's always up to you. So now to reflect over the x-axis, notice we just toss a negative on the outside there. So negative f4 of x. So that equals negative, and then we have this whole big quantity. So you get square root of negative 1/2 x minus 7, and then we have a minus 8. And the reason why this minus distributes to that minus 8, because when you reflect this, granted it'll be over here a little bit further, you'll have this going on. But so then when you reflect it the other way, you'll have that same sort of y coordinate, but notice we've shifted up, and then we're going down that way. Okay, so this whole thing, we'll call this, what do we said this is g of x. So g of x equals negative, and I'll actually distribute it this time. So square root of negative 1/2 x, and notice I dropped the parentheses, so I'll make that a plus 7. And then minus a minus 8 makes a plus 8. So, or you could leave it in the parentheses. That works out as well too. Oh, and I think I just realized I might have forgot to change. Yeah, I wrote F3, so actually let me write this. Sorry, I said g of x is the graph that we're finally finishing with, so I'll put g of x right there. So sorry about that, I forgot to put the g of x, but at the end of the day, I don't think that's going to make or break you come time for exams, so you don't even have to label the g of x, but just want to make sure we're all on the same page. Okay, average rate of change now. So this can trip people up. I'm going to go through, and if there's any more questions about transformations of functions, hopefully that cleared the air, but if not, let me know. I'm happy to help. So what is the average rate of change of f of x from x equals a to x equals b? So you see this line hanging out there, and so I'll call this line L1. All that means is what is the slope? And the cool part here is if the function's f of x and you have that point a, you know that a is the x coordinate and then f of a is the y. In a similar manner, if b is the x coordinate here, this is b and it's f of b. So in order to find average rate of change, it's actually a really kind of simple formula. I'll write AROC for average rate of change. So this is slope. You always go y2 minus y1, so it'll go f of b minus f of a all over. As long as I chose the b first, that means I have to start with b here. So f of b minus f of a all over b minus a. So that's all it is. It's just the slope of what we call a secant line. Now, for those of you that actually go on to calculus, you start talking about slope of a tangent line. So that's, rather than hitting 2 points on the curve, it only hits 1. So that's kind of a cool concept that you get into, so you can get into instantaneous rates of change for those of you that need to go on. So keeping that in mind, remember our formula, we just take f of b minus f of a all over b minus a. That's it, as long as you're consistent with your points. So notice in this case we'll need f of 5 if we're finding the average rate of change. So f of 5 is 5 squared minus 3 times 5 plus 6. So that's 25 minus 15 is 10 plus 6 is 16. And then we need f of negative 2. So that goes negative 2 the quantity squared minus 3 times negative 2 plus 6. So notice that's going to be 4, and then plus 6 is 10. Did I do that right? 4, yeah. Plus 6 is 10, plus another 6. So that equals 16 as well. So notice on this case, that's kind of funny. I chose these numbers at random, to be honest with you, so I didn't anticipate picking two numbers that were identical. So in this case, you get 16 minus 16 all over 7. But either way, that just becomes 0. So what that means is they're both equal, so you have a horizontal secant line. Okay. Now on the g of x one, let's see what happens there. This one hopefully be a little bit more interesting. I got to figure out g of 3. So you go 4 minus 3 times 3 all over 7 minus 2 times 3. And so that equals 4 minus 9, which is negative 5. And then 7 minus 6, which is 1. Hey, that's an easy one, negative 5. And then we need g of 1. Okay, so you get 4 minus 3 times 1 all over 7 minus 2 times 1. So notice you get 1 over 5, 1/5. So now, when we find the average rate of change, should label that. So average rate of change equals g of 3 minus g of 1 all over 3 minus 1. And so that is -5 minus 1/5 all over 2. If you want to do this and make it a little bit easier on yourself, if you don't like fractions, there's an easy way to solve this in your head. Multiply the top and bottom by 5. Notice, and you got to distribute that to both terms though. So notice that makes -25 minus 1 all over 10. And so that makes -26 over 10. And I don't know much, but I know how to do that one. That's -2.6. Okay. Hopefully that makes sense on the average rate of change and how that works. So now moving forward, evaluate the following piecewise function at the stated points. So I'll give you a shot as to how this stuff works after the first one. So f of -2. So notice my x value is -2. So I'm trying to figure out which one of these cases satisfies that. So is -2 less than -1? Well, yes. So what does that mean? That means we can use this function. Notice it doesn't satisfy any of the other three, so we don't even worry about those functions. So here's all you do. You go -2 minus 3 equals, and so notice you get absolute value of -5, which equals +5. So for another eagle egg here, what's f of -1 equal? See if you can get it. First person to answer gets the points. And I see a question up here. Going back to finding the domain, would having a 0 in the numerator... Okay, so going back to finding the domain, would having a 0 in the numerator give you another answer that what it can't be equal to? Actually, so that's a great question. So if you're going back to a domain question and your numerator equals 0, that's not a problem. So that doesn't affect the domain whatsoever. The numerator has no effect on the domain. It could affect your range, but no effect on the domain whatsoever. So you never have to even check the zeros in the numerator for the domain questions. Does that make sense then, Josh, hopefully? And so I don't see any answers for f of -1. I wanted to give you all a shot, so I guess I'll shout it out. Which one does this satisfy in the meantime? And Josh, if that doesn't make sense, just let me know. I'll be happy to answer that one too, a little bit more in depth. So of the scenarios, notice -1 is not less than -1. Okay, good. I'm glad that answered the question. But -1 does equal -1. So we have a winner chicken dinner right there. So here's what we do. We look and we plug in for the x. Oh wait, there's not an x. So our answer is 2. That's it. Okay. So now on the f of 0, we can do the same thing. Which one does that satisfy? Notice it's not the first one, it's not the second one. Oh, 0, it falls in here. So what we'll have to do is we'll plug it in for that x. So we get 0 squared, which equals 0. Okay. Next one, f of 1. So notice 1 doesn't fit in the first category. It's not less than -1. 1 does not equal -1. 1 does fall in between -1 and 2. So we're going to use that third equation again. So you get 1 squared, and that equals 1 as well. F of 2. Notice 2 is not less than -1. 2 does not equal -1. So it doesn't satisfy the first two. But 2 is... Notice we have -1 less than x, but less than or equal to 2. So it satisfies that condition. So we go 2 squared, which equals 4. Okay, so on and so forth. Now here we go for 3. So 3 is not less than -1. 3 does not equal -1. 3 is not between -1 and 2, so it's out of this one now. But 3 is greater than 2, so we plug it into that fourth equation. You get 4 minus 3, which equals 1. Now, one last bit on this, just so we can kind of see what happens. Let me actually draw this out. So we have 1, 2, 3, 1. I'll toss that up there too. Now usually, like the absolute value of x minus 3 makes a v. But what we've done is we shifted this function, the reason why it's appearing here, that's a transformation of x minus the absolute value of x. We've shifted it right 3 units. Okay, so when you do that, you're left with this little piece that looks like just the straight line of the v on the left hand side when we start at -1. And notice if you plug in -1 into this equation, so -1 minus 3, if we take the absolute value, notice that equals +4. So if we go to -1 and that +4, we get that, and then we get basically a straight line that kind of goes up 1 unit at a time from there. So there's that part of the drawing. I'm not saying you're going to have to draw this, but hopefully this will make a little more sense as to what's going on. When x equals -1, you have 2. So what we do is at x equals -1, we put that spot 2. Now, on the other end, for x squared, notice that's a parabola. We should know what that looks like. And -1, the quantity squared, equals +1. So you'll have a hole right there, and it starts to go like this, and then you have that piece. And then at 2, you can notice that that should be 4. And the way we can do that is 2 squared, which we already had calculated. That equals 4. And so there's part of our parabola. And now for the last piece, 4 minus x, when x is greater than 2. So if you plug in 4 minus 2, we'll have a hole here at 2. So we have 2, 2. And then it's decreasing 1 unit at a time, and then so on and so forth. And there's our graph. That's the graph of the full piecewise function. Notice I didn't have a, I promise you, I know you can't see my end, but I didn't have a calculator or anything like that. You can draw these, and hopefully we can start to get some information from that. I actually have a series of videos on piecewise functions and piecewise equations. You use them, whether you realize it or not. Taxes, that's just basically a piecewise function. That's all there is to it. So they do pop up in real life quite a bit, but in terms of mathematically, a lot of people get scared of them at first. So let's take a look at this problem. Locate the intercepts of the following function. So you have f of x equals this quantity x minus 2 squared minus 4, 5x, and that's only if x is less than -4. Then you have 5x plus 2, and then you have the 17, and then you have the square root of x minus 6. So the easiest one, though, of all these is the y-intercept. And why is that easy? Well, because all that is just f of 0. So you plug in 0, that's it, done. Bada boom, bada bing. So when we plug in 0, notice which case does that fall under? That falls under this case, our second scenario. It's between -4 and 1. So we have 5 times 0 plus 2. Notice that equals 2. So our y-intercept is located at the point, I don't know what happened there, 0, 2. So now for our work for the x-intercepts, I'm actually going to need to do some work on the side here. Because first off, we'll set each of these equations equal to 0. So x minus 2, the quantity squared minus 4, equals 0. And I'll give a little space. I'll do 5x plus 2 equals 0. I'll do 17 equals 0. And then I'll do the square root of x, plus 6. I wanted that to be defined, so that's why I changed it to a plus 6. Sorry about that. So make sure you see that square root of x plus 6 rather than minus 6 equals 0. So now we solve each one. The first one, notice you get x minus 2 squared equals 4. So x minus 2, when you take the square root, you got to toss in a plus or minus. So x minus 2 equals plus or minus 2. Okay. So what does that mean? Well, that means x equals, there's two possibilities here. So if you add 2 to both sides, you get 4, or in the case where it's positive, or 0 when it's negative 2 plus 2. But notice that neither of those satisfy our conditions of x less than negative 4. So because neither of these numbers work, the 0 and the 4 do not match in there. So what that tells us is this one will not be involved with our x-intercepts. So 5x plus 2, let's see how that works. Well, notice you get 5x equals negative 2, so x equals negative 2/5. Does negative 2/5 satisfy this condition where we have negative 4 less than or equal to x less than or equal to 1? Well, yeah. So in that case, we do have an x-intercept. And where is that x-intercept? Well, it's going to be negative 2/5, comma 0. Okay, does 17 equal 0? Well, that's just nonsense, right? The constant can't ever be equal to 0. So, and then the other case, notice we can square both sides. You get x plus 6 equals 0. And so x equals negative 6. But notice negative 6 is not greater than or equal to 2, right? So that means this one's out. So our y-intercept is 0, 2. Our x-intercept is negative 2/5, 0. Just because I had one of each here doesn't mean that's going to be the case. Sometimes you can have neither. Right? You might not have a y-intercept nor an x-intercept. Sometimes you might have 10 x-intercepts and one y-intercept. Sometimes you might have just one y-intercept, no x-intercepts. So all those scenarios can happen. Just be aware of how we kind of looked back at that original problem. Okay. So that kind of wraps up most of what I had planned, but there was one more question about inverses. So let's see if I can kind of explain how this works. Let's go find the inverse. Let me know, do you want a medium, hard one, easy one? What are you kind of looking for in finding the inverse? Find the inverse of the, in order for an inverse to exist, by the way, we need it to be 1 to 1. That's actually a main component there. So find the inverse of the 1 to 1 function. I'll just let us know that it's 1 to 1. Okay, so we'll start off easy. We'll go 3x minus 7. Okay, so in order to find the inverse, you have a series of steps. I might use a different series of steps than what your book uses, but I kind of, if it ain't broke, don't fix it. There's other methods to find the inverse, but the first thing I do, this is the easy step, is replace f of x with y. Okay, so what does that look like? Well, so it goes y equals 3x minus 7. Step 2. This is the trickiest part. Solve for x. Sounds easy, right? But it really can be the trickiest part of these problems. So in this case, you get y plus 7 equals 3x. Okay, so then after that, we can divide both sides by 3, and we get y plus 7 divided by 3 equals x. Okay, so we solve for x. In step 3, this is the easiest part, but the most forgotten about. Well, the second easiest part. Step 1 is pretty easy. So the third step, first off, you replace x with the f inverse of x, and then after you do that, and replace y with x. So x has become f inverse of x, and then the y has been replaced with x. And you are done. Okay, so there's some things to be said about inverses, some properties of inverses. If you're talking the drawings of inverses, there's a magical thing that goes on there. So let's say we look at a function. You all recognize what that function is? Let me know if you do. So this is y equals x cubed. And then if we're to try and get the inverse of this, oh crud, don't let your eyes fool you, this is supposed to be a straight line, and not just any straight line. I don't know why when I'm dragging my pen it's kind of going off the beaten path here. That's the line y equals x. And in order to draw the inverse, what you do is you basically just reflect everything over that line. And so that line was supposed to hit, say, right here. And so you get this sort of thing happening. And then, let's say it hit right there. And that sort of thing happening. And this function, that's not drawn completely to scale, happens to be y equals the cube root of x, which is the inverses. So let me actually write it this way. So we have f of x and f inverse of x. And the main property that I want you to take home on this is if AB is on the graph of f of x, then this reflection over y equals x, what that does is that says that BA is on the graph of f inverse of x. Okay. So hopefully that helps with that idea of the connections between these two. You're basically reversing the x and y roles. That's all there is to it with an inverse. Just doing that reverse process. I'll finish with one more. I will do a hard one just for the sake of doing a harder inverse so you can see it. Find the inverse and you're welcome. That's what I'm here for, is just to help out. Find the inverse of the one-to-one function. Let's say g of x equals, so this starts to trip people up, 4x minus 7 and then 5 plus 9x. Okay. So what's that first step? So we'll take step 1. Replace, now we no longer have f of x, but we'll replace g of x with y. So we get y equals, and I'll write that up here, y equals 4x minus 7 over 5 plus 9x. What's our second step? Solve for x. As I said, it might not seem like it, but it is the hardest step usually. So how do we solve for x in this case? Well, what makes this problem hard to solve? Well, the fact that you have a fraction. So what we do is we get rid of it. We multiply both sides by what's in the denominator. So you get y times 5 plus 9x. equals 4x minus 7. So now, in order to solve for x, we have x's on both sides, so you can't solve for it just yet. So we're going to need to distribute this y to both terms. So you get 5y plus 9xy equals 4x minus 7. And anytime you try and solve for a variable, in this case x, you try and get all, if it's a linear term in terms of that variable, so notice x is just raised to the first power, which is the case here, you just get all those terms onto one side of the equation. So we're going to move all the x's over to one side, everything that's not an x to the other. So I can rewrite this as 5y plus 7 equals 4x minus 9xy. If I move too fast, just let me know. That's what I'm here to slow it down and kind of show you if need be. So we're trying to solve for x, and in order to do that, we have x's in both of those terms. So what that means we can do is we can factor that x out. So 5y plus 7 equals x times, well, x times what gives us 4x? Well, it's 4. And then x times what gives us 9xy? Well, it'll be 9y. Now, in order to solve for x, all we do is just divide both sides. So we get 5y plus 7 divided by 4 minus 9y. And that brings us to step 3, because we have solved for x now. And in this case, instead of f of x, we're going to replace x with the inverse of g of x. And after we do that, we replace y with x. So in this case, we get 5x, well, here, let me, before I get into that, I don't want to make it too confusing. Go g inverse of x, then we have 5x plus 7 all over 4 minus 9x. And that is it. Okay, hopefully that helped out, and hopefully this adds to your knowledge a little bit and makes things a little bit easier for you. If you do have any questions in the future, there's a YouTube live discussion board. You can just post them in there, and I probably won't use exactly the same numbers. I'll alter things slightly, but I'll be addressing questions from what's appearing in there throughout the semester. So we'll be having live sessions, hopefully about once a week, if not more often, or less often if y'all don't want them. Just whatever works for y'all. I'm here to help. So hopefully this helped. Y'all have a good night.